Hello and welcome to Cadence Design Systems Fidelity Tutorial Tuesday, where we show you how to use a feature or demonstrate a technique in just a few minutes. Today we are going to show how to set up and run a typical mesh rotation case in Fidelity LES. We are going to use the S76 rotor case. This geometry can be downloaded from the HVAB website as well as on the tutorials page of our website. A typical mesh rotation case is usually split into two parts, a rotating part and a stationary part. We are going to go through how to set up each of these parts. We are going to work on the rotating part first. We are going to use the command charleslaunch.sh, surfer.exe, and then with the flag surf sbin, and then point it to the actual binary geometry file. And the --i is to make it interactive to load the geometry into our surfer instance. Now, if we load the Connect app, we are able to see our geometry loaded here. Here you can see the image of the geometry with the blades and then the pod, which is like the hub. You can actually see the number of zones here. We have 2 zones, the blade, and then the hull. Next, we are going to create a cylinder which is going to serve as an interface between the rotating and stationary part. To do this, we are going to use the command serve cylinder, the XYZ of the minimum, XYZ of the maximum, the radius, and then the refinement, so the number of points around the circle, which is N1024. So now when you hit enter, you're going to see a new zone which is called T-cone by default here. Next, we are going to rename this T-cone to a desirable name. For us, you're going to call it disk. Hit apply. To show the inside of this, we can actually go to views, blanking, then hit apply. And we can actually see inside the geometry to see how the coloring is. So note that any silver means that it's a fluid touching zone, and when it is gold, it is not fluid touching. So we want the cylinder to have silver inside and gold outside so that we have the mesh generated inside the cylinder for this case. So now that we've ensured the right orientation, we can delete the blanking and then save this geometry or this case as an S-bin. To do that, we are going to go to Surfer, Surface Manipulation, Export, and put a name for the S-bin. Then hit Apply, and it's going to write the surface into the directory. Back in the terminal, you can verify that the geometry was written by looking at the files here. You can see that the one that we wrote with disk is written here. Now we are going to try to work on the stationary part. We're going to launch the surfer.exe into the Connect app by using the exact same command, surfer.exe with the interactive flag. Make sure that it is in the interactive mode, as you can see here. Now in the Connect app, you're going to work on the stationary part. First, you're going to create a cylinder that's going to be the outer domain of our computational mesh. Again, you're going to use a serve cylinder, 00 minus 10, that's the depth of it. 005 is the height of it, and then the radius is 10. We're going to hit enter. Then we have our outer domain cylinder here. Again, you can see the gold color means that the fluid is not touching this part of it, and hence it's touching inside of it. Next, we are going to split this cylinder into different subzones, that is inside, outside, walls, by using the command split_flag by angle 150 subzone 0. Now this subzone 0 is basically the subzone that corresponds to the cylinder that we created here. So when you hit enter, you're going to basically get 3 surfaces. So you went from 1 to 3 total subzones. So when you click on it now, you can see that we have one subzone here, one subzone there, and then another subzone below it right here. So now we can move these subzones into its own zones by select the first one, right click, move to zone, click on that button. Then this is going to be C0. Then we have this one here. We are going to name this, clear that, okay. Go here, move to zone, go down here. I'm going to call this outer. And the last one at the bottom is going to be Z1. Move to zone, Z1. So now we have 3 zones out of this. Next, we are going to work on generating the exact same interface cylinder that we did for the rotating part. We are going to use the exact same command, but with the extra flag called flip. This is so that we can get the opposite of the surface that we did for the rotating part. So now when you hit enter, and for now let me hide the outer, you can see that here we have the outside of this cylinder to be silver. That means that we are going to be meshing outside it. This is the fluid touching part of it, and this is opposite to that of the rotating part. And this is what we want for a typical rotating type mesh setup. So again, we are going to rename this zone as disk, the same as we did for the rotating part. Then once you are satisfied with this configuration, you are going to save this whole setup into a new SBin. So I'm going to go again to export. Now we are going to work on the meshing strategy here. Much like this geometry preparation, we are going to have two mesh setups, one for the rotating part and one for the stationary part. This time around, we are going to be using the input files to generate the mesh. So first, you're going to look at the rotating mesh, which is going to be stitch.rotating.in. So now here, we're going to look at the commands that we need in this script. The first line is used to load the geometry in the mesh context. We are going to be specifying the interface zones as disk, which we specified in the SBin file. The HCP delta basically means the background mesh size, and here is based on whatever units your geometry is. The HCP windows are basically the refinement windows that we are going to be specifying the refinement levels for each of these parts, which is the disk, the blade, and then the hull for different levels. The HCP window T-cone is a conical refinement window around whatever region you want. The end smooth is basically where you actually generate the mesh itself. So we can basically do some iterations before the end smooth, and after the end smooth, the mesh is going to be built. So for this case, you're going to put an eye just before the mesh is generated so we can actually see the mesh before it gets built. Now we are going to exit out of this. Okay, to launch the mesh generation, you're going to use the CharLES launch and then specify the number of processors, stitch.exe. Then you're going to put the -i to pass it to the input file, stitch.rotating.in. And if you want, you can actually put it into a log file this way. So here you can see that after you hit enter, you can see all the parameters being processed, all the commands. You can see that it processed the HCP delta, it loaded the geometry, added all the refinement windows that we needed, and it stopped at where we put the eye, which is the interactive. So now here, I'm going to move on to the Connect app and then see what we have. So now in the Connect app, we have the rotating geometry shown here. And if you want to do some analysis, you can actually go into the stitch here, go to refinement windows, and you can actually visualize all the refinements that you wanted or you put there. You can actually edit the refinement levels here, but we don't want to do that because we did that already in the script. So now we can just go here, data, plane data. You can do a plane cut. So X, enter. So then now we can do some views, settings, look at the views here. We can rotate it so we can see the right angles. We can zoom in, let's put this up, update, and you can see the mesh that we've generated here. So we can even zoom in even closer to the near blade region. And once we are satisfied, because we already have the script, you can just go to workflow, hold off, and then it's going to continue to build the actual mesh. So now when you go back to the command window, you can actually see the mesh being built in real time. And right now it's working on all the various levels that is needed until it's completed. So once it is done, you can see here it's going to write out the MLES, which is the mesh LES file. That's S76_rotor swept, tapered.mles in our directory. Similarly, we are going to be looking at the same mesh generation for the stationary part. So if you look at the stationary.input file, again, we are going to be loading in the geometry we already generated. We're going to have the interface zone specified as disk. And then again, the same background mesh specification. And for this case, we only have the disk in the geometry. So we're just going to generate the same level of refinement for that disk, smooth the mesh, and then export it out. And again, to run this, we're going to use the exact same command as we did for the rotating part, but just change the input file to stationary.input and hit enter, and it's going to actually generate the mesh. So once it's done, we're going to have two mesh files, the stationary MLES file, and then we have the rotating MLES file. So next, we are going to be working on how to set up the case in the solver side. So here is the input file that we need for the solver side. We're going to look at a few entries here. At a later time, we are going to talk into more details, what you can add or remove from this. So for now, we are going to be using this skew ops, which is a skew operator for the moving solver. We need to define a few aliases here for convenience, which is basically to define gamma, the gas constant, the reference pressure, temperature, density, and you can actually use some mathematics to calculate the speed of sound based on these variables that you defined. And here we actually specify the parts that we need for the rotation. So we have here part name main. You're pointing into the directory where the stationary mesh is. And for the rotor, you're going to point it to the same rotating mesh. And then you're going to use motion rotation axis to define the axis, the center of rotation, and then the rotational rate here. If we are starting from scratch like what we are doing now, we can actually use the restart multi-part command. If we have run it for a bit and then we have some Lagrange files which are going to be generated in your first start, you can skip the first start and then just use this command here, restart multi-part, pointing to that Lagrange file. If you have already run it before and you're continuing the solution, you'll use this command here, restart multi-part SLES, which is the solution LES file, which is going to be written out at every number of time steps. Now, the init RUP is basically an initialization of the domain using the row, velocity, and pressure, where you give the values of whatever initialization variables you want. And then here, you actually define the time step that you need for the solution. Also note that you can actually do time step CFL, and then that's going to lock it into a CFL mode where you can do CFL 1 or 2 or 3, depending on how good your measures. But for now, we are going to be doing time step DT as this 1.8e-6. Now, the runtime, you can actually specify either the number of steps or you can specify the runtime. Here, we are using the runtime of 11.9 hours. Basically, we are going to be specifying the subgrid scale model to be the Vreeman subgrid scale model. And again, these are already things that should already be included in your input file. Now, moving on to the boundary conditions, you can specify this characteristic boundary condition with the rho, U, and pressure for the inlet, the outlet, and then the outer, because they are technically the far fields. Then the rotor blade itself, you're going to be using the wall model or algebraic adiabatic function here. And the rotor.hull. Now, here we basically put the hull inside the rotating domain. So we have to actually give it an extra flag to specify that is actually not rotating. So we are going to do the WMALG adiabatic stationary. So what this tells the solver is that even though it's inside the rotating part, it does not rotate. Then of course you're going to specify the interfaces as main.disk and then the rotor.disk as interface. And this is one flag or one command we can use to actually export out the forces on the blade itself, because you're giving it a zone called the blade, and then you can specify the moments here. You can write out several images of different places that you want. And then the last one is basically to write out the solution file at different intervals. For this case, every 100,000 time steps. Now for this case, you're going to be using the moving ideal gas solver. To launch the solver, you're going to use the command shown here. So here is going to be running a few checks before the actual solution runs. It's going to calculate this Q operator, which takes a little bit of time. And after that, it's going to start advancing through time. And that's it. With that, we have set up and run a typical rotating type case. In a later video, we are going to go through how to co-process and post-process some of these results, as you can see here. If you like this video, be sure to click the thumbs up button and subscribe to our channel for more videos like this. If you have any questions, comments, or suggestions, drop us a line below or connect with us via LinkedIn, which is linked below. Thank you and have a pleasant Tuesday.